delta. So these are the fixed value values under the action. And these things, they're twisted, delta twisted G conjugacy classes, right? So this map is only really giving you a way to relate conjugacy classes up to H conjugacy. So transfer only defined up to H. H is, you should think about as HC. Conjugacy. And another way of saying that is stable, right? I don't have time to really get into it, but elements are stable if they're conjugate over the algebraic closure. Stable conjugacy classes. Stable distributions.
Is zero an isomorphism?
No, it's neither injective.
Really?
Maybe injective. No, it's injective, but not so.
Sorry, what?
Isn't TH isomorphic to T delta?
Yeah, but this guy is not isomorphic to that guy. And you have G. Is that true?
I thought that.
Sorry, I really don't think it's an isomorphism. G delta. Yeah, the thing is, this is true. Connected component. Or, sorry, something like this is true.
It's true in the 4 examples you wrote a couple of words back.
Yeah, maybe for GLN, things might be easier. That's possible.
But I mean, I thought this was quite general.
So I think this is the general state, something like this, that the guys fixing that, get an isomorphism here. Anyways, yeah. I don't think it's an isomorphism. Pretty well. Okay, so we're looking for stable distributions coming from packets, right? And when pi phi, if you look back to the original diagram, if the L packet is tempered, and by that I mean that all the representations of these are tempered, then this sum, I'll write the characters like this, trace, I hope no one minds. Pi in pi phi. Then this is stable. This is a character. Distribution character. Dot pi. Otherwise, stable under conjugacy over C. Okay, so if I look at the character and you think of that as a function on GR, if I have two elements that are conjugate over GC and GR, then they have to have the same value on this distribution. So it works if it's tempered, otherwise not necessarily. If pi be not tempered, then this distribution need not be stable. Okay, so in that case, we can't get this endoscopic transfer. Arthur proposed A parameters, some alternative parameters. They look like this. The homomorphisms, again, now we add a copy of SL2 into G, so the extra conditions on there, skip those. A parameters, A packets that correspond to these things. And stable distributions. I call it beta C. Okay, so for some non-tempered representations, things that should somehow appear in automorphic representations, you define such parameters, and then you propose that there should be some sort of packet, some sort of set of irreducible representations that occur in some stable distribution attached to this thing. Right? And this stable distribution, it's not simply a sum, right? It's some sort of virtuous sum of the representations occurring, but it is stable. And then there are all these other conditions that this should satisfy, particularly should satisfy endoscopic identities, unitarity assumption, so on and so forth. So he proposed this in some generality in the 80s, and then 5 years ago or so, he proved that for twisted endoscopy of GLN, the kind that I pointed out, slightly more generally, these things exist. Now, but the problem is, it's not so easy, even for R, to see what these things are. Okay, so blue marker. And okay, those are hard. And what I'd like to do is give you an idea of how you can use Atlas to compute these things for fixed parameters in the time that I have left. Fortunately, there's there's a ways to go. There's still some more theory I have to cover. Yeah.
After you started at 1:30, so I mean, if you run out of time, you can take a break and then you can finish. So don't be rushed.
Okay. Okay. Thank you. Maybe I don't want to erase that. Yeah, I can put some more stuff over here. So there's some important, nice cases for GLM. For GLM, everything is stable. So all conjugacy classes are stable conjugacy classes. It's Gaussian canonical form. And the L packets and A packets are known. And they're singletons. Something like that. It's just a prescribed way of getting this guy from this parameter. The obvious thing that it should be to look at automorphic representations. So everything is nice for GLNR, and this is why twisted endoscopy for GLNR is valuable, because the L packets are small. You can get a good handle on those guys, and use twisted endoscopy to say something about the A packets for the endoscopic groups. Okay.
First, an autobahn is
Yeah, if you ignore this guy, so every the condition here is that if you restrict to that thing, that has to be a tempered L parameter. Okay. So it includes the L parameters of a tempered. I think I should find this.
Use the same symbol.
Use the same symbol.
They're
Usually,
both a single code. They come from the same data instance.
well, so I'm not sure I understand the
So
question.
you have two type of packets.
Yes.
You can say that they come from the same thing. Can identify them.
Well, not quite. So in the case of a tempered L packet, that's a special case of an A packet. Not every irreducible representation is an A packet. Those are special ones. Yeah, they're different in that way. And one more nice thing is that the pseudo-L packets, and this is crucial for what follows, the pseudo-L packets, which look like this, are always stable. In the sense that if you take the sum of the characters of representations, as I did earlier on for the tempered guys, right, that sum is stable for any G. Okay, so I have to talk about twisted characters. Suppose pi is a representation of GR. Such that, well, let's say irreducible. I don't really want just irreducible, but okay, let's do that and just say it in a few words. Such that it's stable under composition with the outer automorphism. Okay, and let's give a name to an intertwining operator. Okay, if pi is irreducible, then A is unique up to multiplication by non-zero scalar. And if we further make the assumption that A squared is equal to 1, then we have two possibilities for this differing by plus or minus 1. We're talking about this before. We both talked before me today. So then we have two extensions of pi to the extended group generated by delta and GR. And they're defined in the way that I mentioned, that two extensions of this that are defined by pi delta is equal to A, or pi delta equals minus A. And why should one choose one over the other? Well, the only way you can answer that question for something like GLM is if you have some sort of extra data. So Arthur solved this problem by choosing a Whittaker datum, so basically an upper triangular Borel, and a character, a non-degenerate character on the unitopic radical. And that gives you a Whittaker datum, some sort of preferred information, and that gives you a Whittaker model, and this is Whittaker functionals are one-dimensional. Once you have a one-dimensional object, and A acts on this one-dimensional object, then it's great because you can normalize things so that norm one vector gets sent to itself by A. Okay, so there's something canonical. And if you look at the Atlas world, there's a similar thing going on there for GLN. For GLN, you use cohomological induction from a torus. This one-dimensional, so it's a abelian group which has a one-dimensional representation upon which delta acts, and then you can choose things to be plus or minus 1 for GLN. Okay, so for GLN, this problem is resolved. One may choose canonical extensions. Okay, can't do that for any group, but for GLN you can.
I'm sorry, can you say again, how do you do it?
Yeah, so in Atlas parameters, if you have E, I can't remember how many things we have here. We got G, L, T, tau, it's a long order, lambda, beta, okay? Always choose L and T to be 0.
So you're saying that for GLN, it's always possible.
This
to
is,
choose zero.
yeah, regular character. Yeah. If you look at the table in the twisted parameters paper, and you apply all of the Hecke operators which are allowed for GLN, so not all of those Hecke operators are allowed, then you'll quickly see in the table that these things in yellow. Okay, that gives you the GLNR. You'll see that all these things are always 0. Okay? And that gives you your preferred canonical guy. And yeah, as you pointed out, it's impossible if you have like 2i, 1, 2, whatever, then signs will flip. Yeah. So this is very special.
The point is, these extended tori that come up,
yeah.
always I mean, the theta fixed things in
Yeah.
GLN always contain this distinguished delta. And so you can just make the extension by making delta act by 1.
That's correct. Yeah, that's equivalent.
That's what the 0 and 0 mean. The fact that 0 is an allowed choice for L means that you can choose the extending element to be delta, and then the fact that 0, well, then choosing that element to act trivially means choosing the tau to be 0.
Yeah, that's exactly, yeah. Okay. Before I forget.
So just to unpack that just a little bit more. So,
yeah.
So here's a naive question, and maybe completely stupid.
No, it's always good.
But does this
Don't
mean?
apologize.
No, you can apologize.
I'm deeply sorry for the discussion. Does it mean that in the rows of the table that we were looking at, the rows of the output of Atlas that we were looking at, that there are always plus signs? Or is that?
Well, yeah, for this, you would take your plus to be defined by this, and then you would always get plus signs, that's right. Yeah. Yeah, you never get flips.
So, but Atlas may not make that choice that you're making.
It does.
Oh, it does?
I check.
Okay.
Or rather, you check.
Yes.
Right? Yeah.
Prefers zeros
No.
over non-zeros.
Now, what does this say about UPQ?
What does it say about
I
UPQ?
mean, I just asked the,
Oh, you mean when you look at Bowman Duality?
That's not allowed. UPQ, these were split groups in that map.
Yeah.
Well, okay, so may I was just making again, just thinking about, very naively about the Hecke algebra. Is there a corresponding statement? So we agreed, or you explained to me, that the output of Atlas in each row only has plus signs. Okay. Now, does that translate into some easy statement about the Hecke algebra action for UPQ? So I understand that that's not the setting that you're talking about.
Yeah.
And that I guess you can't even make these canonical extensions for you.
Yeah, I don't think, yeah, unless,
but-
maybe if you quasi-split UPQ.
But it seems like it should translate to something,
Because of
I don't know.
duality, but
Yeah,
otherwise, I don't think so. I don't think it's yeah, one of the things that we're using here is that all roots are, there are no type 1 roots, they're all type 2. Not in the sense of 1, 2, 3, just the old-fashioned version, or the rainbow version. They're all type 2. And if you have a type 1 root, like UPQ has things like that, then bad things can happen. Right? If you look at the list of... Yeah, so I don't think it can be transferred.
But maybe someone can... It would seem that the Heck algebra action for UPQ in the twisted, naively speaking, the Heck algebra action in the twisted case for UPQ would determine the Heck algebra action for twisted GLN. And
Well,
therefore,
only in the quasi-split case, I think.
or UNN, say.
Yeah, so UNN, I think, yeah, if you want to compare UNN with GL2N, then maybe you could say things through duality.
Okay.
A warning flag here is that the signs on the two sides are not defined symmetrically.
Oh yeah, there's that too.
So there are some nasty surprises when you try and.
Uh,
So it's just a stupid question. I mean, a stupid naive question. So there's some.
It's possible, but it's not. You have to check. I mean, it's possible, but I don't. The other thing is, I think that the fact that you can always think these things to be 0 for GLN is at least partly related to the fact that for UPQ all of the cartons are connected.
Yeah, that's what gives you the type 2 business, right? Okay. There are two types of canonical choices, one from Atlas and one using Whittaker extensions. And the two don't have to agree. In fact, they don't agree. We'll see that. So what's the twisted character? The twisted character. TR delta pi is a distribution so we're really doing analysis here. It's a distribution on compactly supported smooth functions on the non-identity component of this extended group. I think at some point I should say G is equal to GLN. And delta is what it was earlier. So F x delta pi x pi delta, right? So we're assuming that this is chosen canonically in one of the two pictures. It's not really about the differences for the moment. Okay. So that's the distribution. And I'd like to say a word about how this, what this has to do with the casualistic loading polynomials that we were looking at in Jeff's talk. So consider pi plus, okay, an irreducible that G are the extended group. Okay? So the canonical, I just put the plus down below so it looks like before. Okay? So we've got this, this preferred extension to the extended group. And then, as we saw earlier today, we can have a character formula.
This means delta x by a?
Delta x by a, yeah, there's a preferred a.
Okay.
And then the trace, so this is an oxygen group, this thing, right? So we can look at the trace, not the twisted trace, that's coming in a second. I think I got this right.
But in the previous formula, did you want to take the trace of pi of x, pi of delta?
There's a pi missing. And yeah, I think that's okay now.
And the trace of that.
Oh, the trace, sorry, yes, that too. The trace, yes. Length, pi t plus. And then over here we have the multiplicity of, well, not multiplicity, some integer, tau plus I, tau plus, plus, and pi plus tau minus, I, tau minus, and then other stuff. Okay? So assume that tau is also stable and delta and irreducible. This is some sort of, you think of a standard representation, reduced representation, that's why I wrote the I. They occur with some kind of Mezo multiplicity, because it's a character formula, but this is a composition.
So you should say trace in front of those eyes?
Oh, yes, okay, trace. Okay, sorry. Very sloppy. Trace, trace. Thank you. Okay, now you can also think of this type of formula as an identity.
Sum over taus.
Yeah, that's why I put dot, dot, dot.
Okay.
Yeah, it's just, and things that are not fixed. So I'm just trying to say what happens when you have an irreducible data stable tau. Now, you can regard this formula as a distribution formula. It's a distribution on this extended group, a full extended group. And you could also think of it as a function on regular elements of this group. And therefore, you can also restrict it to the non-identity component, to GR times delta, this thing. So think of this as a distribution. And then this whole thing. So restricting to GR, I should say where this is, on GR, comma, delta. So if I just restrict to the non-identity component, then we get something like this on the left-hand side. No, I can't raise it. And I need that. So what's left? Can I move over here? Okay, so we obtain the twisted trace, pi is equal to minus 1 L pi plus, we can keep that there, L tau plus, and then what happens to these two is we also get twisted traces, right? But these things, they differ by the choice of intertwining operator. They differ by plus and minus 1, right? So if you go back to the definition over here, you would replace this guy with tau delta, and you would put a minus tau delta for this thing over here, something like that. And therefore, you get minus signs. Trace delta I pi plus, sorry, tau, and I wrote the wrong thing, so wrote it too soon, minus pi plus tau minus and now trace delta I tau plus. Yeah, okay, I think that's right. All right, so when you restrict to the non-identity component, you're getting the difference of these integers. And if you look at the Atlas paper, you'll see that these things are given by these twisted KLB polynomials. Did I get the pi and the tau in the right order?
You got it in the order that Jeff used first this morning, which is wrong.
Okay, so then we'll do the right thing. For once. Okay. So that's 19.3 something, in case I'm doing this for you, Jeff. Okay, so that's the, in my opinion, the representation of theoretic significance of these twisted conjugative polynomials. They're giving you a decomposition of the twisted trace, not of the extended group, but just the restriction to the non-identity component. So I'm not allowed to erase that either. Yeah, I guess I won't get to the computer stuff before time, but I'll be able to finish the introduction part of things.
And that's a perfect split because we didn't have something.
Sorry about this. I stayed up late last night throwing things together as best I could. Okay, so so much for twisted characters. So now here's some theorems. Due to Arthur and Shelstad and a whole bunch of other people. So the transfer, we still have that diagram in front of you that we have on the board over there. The transfer of these stable things coming from pseudo packets okay? So this, as I mentioned before, is stable. The pseudo packet, the fully induced packets. This thing is equal to just this single guy when you look at the embedding. I'll remind you, epsilon is the embedding of h hat into g hat. So that gives you something like this. This is the singleton.